So, in this lecture we are going to talk about discrete time transfer function and closed loop block diagrams under voltage mode and current mode control. So, here we are first going to talk about step by step derivation of various discrete time transfer functions, then discrete time control to current as well as control to output transfer function, then loop transfer function under digital voltage mode control and the loop transfer function under digital current mode control. So, if you recall, state space modeling of DC-DC converter, if you take a synchronous buck converter with practical parasitic, and we can also consider synchronous boost converter. So, where we can consider inductor current and the capacitor voltage as the state variable, and we can also take input variable as the input voltage and the load current if we consider an additional sinking load. Next, if we want to write the state space model, then based on the switch configuration, whether the Q is the gate signal, whether Q is 1 or 0, we will get accordingly A0 or A1, and here AQ for a buck converter can be written AQ in terms of the parasitic. Here we are assuming that the two switches of the buck converter are identical, so their on state resistance are same. Then the A matrix will be common. You can see the A matrix is independent of Q, but if you take Q BQ, it is a function of Q. That means when the switch is on, then 1 by L, when the switch is off, it is 0, and this particular term is associated with the input voltage, and this particular term is associated with the load current. So, load current, you can see the load current term, there is no Q dependency, but the input voltage there is a Q dependency. So, whether input voltage is connected or disconnected, and we have discussed this derivation in detail in this lecture course in lecture number 33. Now, if we take the synchronous buck converter, and since we are considering this R1 and R2 are equal, because we have taken R1 is equal to R2 equal to R, and where RE we have taken R plus R on, that is RL, that is the DCR of the inductor. Then we can write all A matrix are common. Beyond matrix will be 1 by L term will be there, for B2 it will be 0. If the load sink is not there, if we remove this path, then beyond B2 will be simply like this. So, B2 is a null matrix. And we have also discussed how to derive discrete time large signal model. So, that means we have discussed, even we have discussed in lecture number 33, 34, as well as we have discussed in lecture number 38 about the large signal model, where for a buck converter under trailing edge modulation, interval 2 sampling, this is the delay, and this delay can accommodate the ADC conversion time, controller computation time, as well as the DPWM delay. So, you can write the expression like this, and where output voltage is a function of state multiplied by the C matrix, that means C into X, and the C equivalent matrix also we have discussed. Here we can get the C matrix here. So, what is the C matrix? Okay, let me write down the C matrix. C equivalent. C equivalent for a buck converter is simply alpha RC into alpha, and what is alpha? It is R by R plus RC. Okay. So, that means the C equivalent does not depend on any Q function. Now, discrete time small signal model, that also we have discussed, that if you take the xn plus 1 tilde, which is equal to A equivalent into xn tilde plus B equivalent to D tilde, and similarly V0 tilde will be equal to C equivalent into xn tilde. Then for a buck converter we have discussed A equivalent is AT and B equivalent is A e to the power A equivalent equal to e to the power AT and B equivalent equal to e to the power AT minus, this is the delay, and B1 Vin is the input matrix. What is Bn? We know B1 equal to, in this case, 1 by L 0, Vn into T, and this we have also discussed in lecture number 38 in this course. Now, the discrete times we have to derive the transfer function. So, we have one model, part of state space model and part of output model, all are in discrete time. Then we apply Z transform. If we apply Z transform, then we will get Zi because there is a n plus 1, and then all A equivalent, B equivalents are there, and V0 Z equal to C equivalent to XZ. Now, XZ from this equation, if we write this equation, if you take this term in the left side, you can take XZ tilde common, it will be Zi minus A equivalent into inverse B equivalent into dz. So, that means we can obtain X tilde in terms of D tilde along with the matrix A equivalent, B equivalent and Z. Then xz tilde by dz, D tilde will be this, but this is a 2 cross 1 and this is a scalar. So, we will get a transfer function matrix. Okay? Matrix will be 2 cross 1. That means, what are the 2 cross 1? So, you will get 2 cross 1. The first term will be the current to duty ratio and the second term will be capacitor voltage to duty ratio. That means, if we want to get the current to, so how to extract current from the xz? You simply multiply with 1 0 matrix, then it will give you the first term, because we know what is my xz tilde, it is nothing but ILZ tilde and this is the VC as Z tilde, where VC is the capacitor voltage. So, if you want to take the first element, that means my ILZ tilde is equal to, I will simply multiply with this matrix into xz, and this is exactly what we have done here. Then diz will be simply ILZ by dz, this is 1 0 term will be there, and then whatever we have obtained here we should substitute here, and this is called control to current transfer function. Next, we want to derive control to output transfer function. So, V0n is already a function of xn, that means if we apply Z transform, that means we can get V0z is a function of C equivalent into xz. And what is xz? We know xz tilde equal to Zi minus A equivalent inverse B equivalent into D at Z, and this is exactly shown here. Then if we substitute this into this equation, then we can get this equation. So, it will be C equivalent, then this term will come, and that is your V0 Z by dz, and this is called control to output transfer function. Now, we have derived control to current transfer function, that means we have derived IL to D transfer function in Z domain, and this we call GICZ, control to current. We have also derived control to output transfer function, and this we call GVDZ, right. So, in digital voltage mode control, if we consider what is the block diagram, that means how do you generate duty ratio in a digital voltage mode control? So, that means again you take the sawtooth waveform like this, and there is a modulator gain, and if this is Vn and if this is MC, then what will be our Vm, and this will be our, let us say, our duty ratio D into T. So, then our duty ratio tilde will be Fm into Vm tilde, where Fm is nothing but 1 by MCT, where T is the time period. Okay. This is written MC, and we can express that D tilde Fm this. Now, we will show if we draw the block diagram. If we draw the block diagram, so this is our error voltage, then this error voltage goes to the controller, controller generate the modulating signal, and then it goes to the duty ratio. So, here this Fm is nothing but 1 by mct. Okay. So, if you use a different color, it is 1 by mc into t. This is our Fm. Then we have already derived V0 to D transfer function in Z domain, and that itself take care about the delay and all. And that means if we go back in voltage mode control, you know what we are discussing here, that means what is my Vm? So, that means if you draw the loop, this is our ref and this is our V0Z, and if we keep this thing to be 0 for a regulator purpose, then it goes to our controller and controller gives us Vm pattern, and then this goes to Fm and this gives rise to our D pattern. So, how can I write D pattern in terms of V0? So, it is simply Fm into Gc into minus V0 Z, which is nothing but minus, you can write Gc Fm whatever, Gc Fm V0 Z. And what is V0 Z? V0 Z is nothing but C equivalent into xz. So, you can replace this term here, then you will get this expression. Why we are writing this expression? We want to get the closed loop characteristic equation. That means we have the original equation like this, and this is the original equation irrespective of what control technique we use. If we use a voltage mode control, our duty ratio is being generated from the outer loop, and we have already discussed this expression is function of V0. So, we can substitute here, and we further know this is nothing but minus Gc Fm into C equivalent into xz, and if you substitute, okay, so this is there, that means we can erase this part. Then if we apply Z transform, sorry, it was originally it was in time domain, so now we apply Z transform. So, here we have to substitute this D into this term, and all this expression will be substituted here. So, we will get Gc Fm B equivalent, and this term is actually coming here. That means, if we start with this expression, let us start. Our original expression was x plus 1 is equal to A equivalent xn partas plus B equivalent D parta. If we take the Z transform, then what we will get? Z, Zi because of n plus 1 is equal to A equivalent into xz plus B equivalent into dz. And what is our dz? We have discussed it is minus, that means you can refer here, minus Gc Fm C equivalent into xz. If we replace here, then what will get? Zi xz equal to A equivalent minus Gc Fm C equivalent, this whole thing into x z. And if you take everything in this side, then this is the expression I am showing here, then you get the characteristic equation Zi minus of this, that will be 0. That means, the final expression will be Zi minus A equivalent plus Gc Fm C equivalent this whole thing into xz equal to 0. And if we take this part and if you take the mode. That means, if you take the determinant of this and this determinant equal to 0 is the characteristic equation. What is the role of this characteristic equation? So, the role of this characteristic equation, you have to ensure that the all eigenvalues should be within the unit circle, otherwise it will be unstable. So, while we can derive the stability concept from the loop transfer function, but this way of representation actually makes sure that you do not miss out anything. That means, you can ensure that by suitable choice of controller, you have to make sure that, because it is directly in the digital domain, so none of the eigenvalues should go outside the unit circle, because this is under closed loop voltage mode control. And when we go to design, we will consider such equation. That means, we have to make sure that no eigenvalue. So, if one of the eigenvalue goes outside the unit circle, then it may lead to different type of instability. So, if you take the voltage loop transfer function, that means, we have this loop which will be product of all, then the modulator gain we know it should be MC, MCT, where MC is the compensating ramp, that means sawtooth waveform slope, and the controller we have taken, if we take a PI controller, but typically for voltage mode control we consider a PID controller. So, if you take a digital PID controller, then we will get Gc of Z equal to Kp plus Ki 1 by 1 minus Z inverse plus Kd 1 minus Z inverse. So, this is the discrete time integral term and this is a discrete time derivative term, and these are all coming from the backward difference formula. So, then we can get, and we know that GVD is nothing but C equivalent multiplied by this inverse matrix into B equivalent. So, you can easily get the loop transfer function by substituting here, by substituting controller here, and also by substituting here. So, you can obtain, and then we can draw the loop gain plot to make sure that the closed loop is stable. Similarly, if you take the mixed signal peak current mode control, we can start with the very fundamental equation, that is the perturb model, but in current mode the difference is that the generation of the duty ratio is different. In voltage mode, the duty ratio is generated from the, how it is generated. If you take a controller, the output of the controller is compared with the sawtooth waveform and that generates the duty ratio. But in case of current mode control, it is not like that. So, in current mode control, if you consider, if this is your inductor current, let us say, so here to here we have time period which is fixed, because we are talking about peak current mode fixed frequency control. Then what we can consider here, this is our rising slope and this is our falling slope. Okay. Now, how do you generate duty ratio? So, this is our dt, and if this current is my In beginning of this cycle and this is my In plus 1 and this is my peak current, or here you can write the reference current. I will say it is the reference current. It is the reference current. So, that means my duty ratio can be derived from here, my reference current minus In divided by M1. Okay. So, you can substitute output. So, these are the two basic equations of the state space model. Then we have discussed, that means if we take from here, the duty ratio perturbation can be a function of I ref tilde minus IL tilde, where we can write in terms of modulator gain by this current error. And what is the modulator gain? It is simply 1 by M1t under peak current mode control, where M1 is the rising slope of the inductor current. Then we can write I ref n it is coming out of as a PI controller, because typically for current mode control we take a PI controller, and this is a discrete time PI controller. So this part is the proportional part, and this is coming from the integral part. How is it written? So the integral controller can be written as the previous integral term plus the integral gain into the error voltage, and this is using incremental algorithm or the discrete time integral control. That means if you take the transfer function of the controller, that means the controller output, what is the input to the controller is the error voltage and output is the reference current. And if we want to get the transfer function of this, that means V is Z, which is nothing but our GCZ. So it can be written as Kp plus Ki into 1 by 1 minus Z inverse. Okay. So if we write below to make it clear, it is Ki into 1 by 1 minus Z inverse. So this term will go here. Okay. Next, that means if we apply Z transform, IREF can be written in terms of controller, because if you take the loop transfer function in current mode control, you have a reference voltage perturbation, simply it is 0 for regulator purpose. Then we have this V0 Z perturb, then we have this controller, and this controller generate our reference current. So that means the reference current is simply product of GC into V0 Z. Then V0 Z we know it is nothing but C equivalent into XZ, and this is written here. Next, controller, for a PI controller we know it is Kp plus Ki by 1 minus Z inverse. Now we start with this. So we replace duty ratio. What is duty ratio? We know duty ratio is the modulator gain, then IREF perturbation minus IL perturbation. So if you take in terms of Z, this will be, or if you take so D, if you write in terms of Z, here it is in time domain, so it is just the perturbation. We have learned that D perturbation is Fm into IREF perturbation minus IL perturbation, and that we have substituted here. Then IREF we know it is minus of this, and what is IL? We know that IL is nothing but 1 0 matrix into X. So after Z transformation we have to write this, that means we are writing this. So that means if we apply Z transformation on this equation, what we will get, or let us write from the beginning. So that means we have x n plus 1 A equivalent into x n plus B equivalent into d z. Then what is d z? This is nothing but Fm into IREF z minus, or IREF into IL. Then what is IL? IL is nothing but 1 0 into xn. Then so if we apply, that means we apply here Z transform, that means it will be Zi into xz, left side will be A equivalent into xz plus B equivalent into what we will get. So Fm, then IREF Z. So we can write this out. Let me write this term below. So it is B equivalent into Fm. Now, what is Iref Z? Iref Z is minus Gc into C equivalent into Xz. So, if we write Z domain, so this is Z. That means, so here it will be what? Iref Z minus IL Z. So, what is IL Z? That means this you replace with this and this you replace with this, and after that you will get the overall characteristic equation, and you can take everything in the left side because xz can be taken common. So, you will get the characteristic polynomial like this, and this equation is the characteristic equation. So, from here you can find out the eigenvalues to check whether all are inside the unit circle or not. So, that means this is a loop transfer function under peak current mode control. You see, this is the reference voltage minus the current voltage, output voltage. This is the error voltage, goes to the controller, it generates the reference current level. Then this reference current level minus IL is nothing but your error current, and if you multiply with the modulator gain, it will generate the duty ratio, because we know that duty ratio is nothing but Fm Iref minus IL. Now, how IL and D are related? It is nothing but the control to current transfer function, right? And then how output and duty ratio is related? It is nothing but the control to output transfer function. So, you will get the complete loop transfer function. Now, if we want to write, so you can see there are two loops. One loop, this is the inner current loop. This is the inner current loop, and this is the outer voltage loop. So, it is a two loop control. So, you can get the loop transfer function by block diagram reduction, the complete loop transfer function, where the modulator gain is 1 by Fm and the control is the PI controller. So, we can obtain the loop transfer function of the current mode control, and this will be used when you want to design the controller in the subsequent week. And this is the GVD of this GVD, that also we know. So, that means in digital current mode control, you can accurately get all the small signal transfer function very easily by just applying the Z transformation. And control to output transfer function, you know, the current to control to current transfer function. So, it is 1 0 matrix has to be multiplied with this term, okay, and this will be a scalar quantity. So, in summary, we have discussed step by step derivation of various transfer function. We have talked about discrete time control to output, control to current as well as control to output transfer function. Then we have derived loop transfer function under digital voltage mode control, and we have also derived loop transfer function, we have shown how to derive loop transfer function under digital current mode control. So, this loop transfer function derivation, and after getting the loop transfer function by using various transfer function, control to output, control to current, we will be using this transfer function for the design of both voltage mode, digital voltage mode and current mode control, and subsequently we will also implement that digital controller using Verilog HDL, and we will prototype using FPGA, and we will also show hardware case study for buck and boost converter for voltage mode and current mode control. So, I want to finish it here. Thank you very much.